The space between the stars is not empty at all. It is filled with a strange and dynamic substance astronomers call the interstellar medium. Think of it not as a void, but as a vast cosmic ocean, one made of thin gas, bizarre dust, and invisible forces. This ocean holds secrets that rewrite our understanding of where planets come from and even how life might begin. By the end of our journey, you will see the galaxy not as a collection of lonely stars, but as a single, breathing entity. We are floating inside a puzzle where dust grains hold unknown chemistry and clouds of gas move with a mind of their own. What do you believe is hidden in the darkness between the lights? This cosmic ocean begins with a whisper, not a roar. Before we can see the stars, we must look at what blocks our view. The first great mystery of the interstellar medium is the very dust that drifts between the lights. We call it cosmic dust, but that name is almost an insult to its complexity. These are not simple specks of dirt. They are intricate grains, smaller than a wavelength of light, forged in the violent deaths of ancient suns. When a massive star explodes as a supernova, it scatters the elements of its core across space. In those expanding clouds of stellar ash, under conditions we can scarcely replicate, atoms of silicon, carbon, and iron slowly cling together. They form microscopic motes of silicate rock and graphite, the soot of the cosmos. Other grains condense in the gentler, persistent winds blowing from aging red giant stars. Yet for all we know about their origins, their exact recipe is unknown. What strange combinations of minerals and ices coat their surfaces? What molecules, the potential building blocks for life, might be clinging to a single, frozen dust grain right now? This dust is far from a passive curtain. It is an active and deceptive player. At temperatures just a few degrees above absolute zero, these grains exhibit bizarre properties. They can act as tiny chemical laboratories where simple atoms meet on their frigid surfaces and fuse into complex organic compounds. They are the seeds of future worlds. Over millions of years, gravity pulls these grains together into clumps, then rocks, then planetesimals, the very bedrock of planets. Yet this vital dust is also our greatest obstacle. It scatters and absorbs starlight, creating those dark ribbons and blotches you see in images of the Milky Way. To peer through it, astronomers must listen with different ears, using infrared telescopes that see the dust's own faint heat glow. In those ghostly infrared maps, the dark becomes bright, revealing swirling nurseries where dust is thickest. So the very substance that hides the universe's secrets is also the substance that builds new solar systems and possibly the ingredients for biology. The first mystery is a paradox. We are made of stardust, yet we must constantly look past it to see our own origins. What might we be missing, hidden within those countless shadowy grains? But if dust is the shadow, then what are the fingerprints left in the light itself? For over a century, astronomers have been staring at a spectral ghost story. When they break the light from distant stars into its rainbow of colors, they find not a smooth spectrum, but one scarred by hundreds of dark, narrow lines. These are not the familiar lines caused by simple atoms like hydrogen or helium. These are something else entirely. They are called the diffuse interstellar bands, and they are one of the oldest unsolved mysteries in all of astrophysics. Think of starlight as a messenger traveling for hundreds of light years to reach our telescopes. Along its journey, it passes through the vast clouds of the interstellar medium. Certain molecules in those clouds are tuned to absorb very specific colors of that light, like a radio picking up one station and blocking another. The dark bands are the missing stations, the colors that were stolen during the journey. The problem is, we have the list of stolen colors, but we cannot find the thieves. We have catalogued over 500 of these bands, and for the vast majority, we have no definitive match to any known molecule on Earth or in our laboratories. The leading suspects are large, complex carbon-based molecules, perhaps shaped like soccer balls or flat sheets. These could be polycyclic aromatic hydrocarbons, the same kind of compounds found in soot, or even fullerenes, the famous buckyballs. But the evidence is circumstantial. It is a cosmic detective story where the clues are shadows and the suspects are invisible. This matters profoundly because these mysterious molecules are tracers of the galaxy's hidden chemical complexity. They are proof that the space between stars is not just a soup of simple atoms, but a rich chemical reservoir, potentially brewing compounds that are the precursors to the chemistry of life. Solving this puzzle is a painstaking dance between the telescope and the lab. Astronomers measure the exact wavelengths of the bands with incredible precision, and then chemists on Earth try to recreate the harsh conditions of interstellar space, the extreme cold, the vacuum, the bombardment by starlight, to see if they can make a molecule that produces the exact same dark line. It is a search for a key to fit a lock we cannot see, a testament to the fact that even the darkness between the stars has a chemical signature we are only beginning to decipher. What could these molecules be, and what are they telling us about the universe's capacity for building complexity in the most unexpected places? The dark bands in starlight are a haunting clue, but the chemical story of the interstellar medium holds an even more profound surprise. Deep within the cold, sprawling clouds like Sagittarius B2, near the center of our galaxy, radio telescopes have picked up a faint, specific hum. This is not random noise. It is the vibrational signature of molecules, and the list of what they have found reads like the inventory of a cosmic pharmacy. Ethanol, the alcohol in drinks. Glycolaldehyde, a simple sugar. Formic acid, the compound in ant stings. Even the ringed structure of benzene. These are complex organic molecules, some with a dozen atoms or more, and they are floating freely in the emptiness between stars. This discovery shatters our old assumptions. For decades, we thought such intricate chemistry required the warm, dense, protective environment of a planet, a place with liquid water and an atmosphere. Space is neither warm nor dense. It is a near-perfect vacuum, bitterly cold, and bathed in harsh radiation that should tear delicate molecules apart. Yet there they are. So how does a molecule like sugar form in a place more hostile than any desert on Earth? The answer lies on the surfaces of those mysterious dust grains we discussed. In the deep chill of a molecular cloud, a single atom, perhaps carbon or oxygen, drifts until it sticks to a microscopic grain of silicate or graphite. It sits there, frozen in place. Over centuries, another atom bumps into the same grain and sticks beside it. On this impossibly tiny, frigid stage, a slow-motion dance begins. The extreme cold actually helps. It prevents the atoms from bouncing away, giving them time, immense stretches of time, to react and form bonds. Occasional bursts of energy from a passing cosmic ray or a photon of starlight can provide the spark needed to rearrange them into something more complex. Layer by layer, atom by atom, these ices build up on the dust, forming a frosty mantle that becomes a primordial chemical factory. Eventually, the heat from a newborn star nearby can blast this mantle away, releasing a soup of newly forged organic molecules into the surrounding gas where our telescopes can finally detect them. The implication is staggering. The fundamental ingredients for biochemistry, the very scaffolds upon which life is built, are not exclusive to planets. They are being manufactured on an industrial scale across the galaxy, in the dark, cold clouds that birth stars. This forces us to ask a revolutionary question. When the young Earth was still a molten ball, constantly bombarded by comets and asteroids, was it also being seeded with a rich delivery of pre-built organic compounds? Did the sugar for the first strands of RNA, or the acids for early metabolism, literally rain down from the heavens? It suggests that the universe, in its vast and seemingly indifferent processes, may be inherently predisposed to create the conditions for life. The interstellar medium is not just a nursery for stars. It is a universal kitchen, quietly preparing the recipe for complexity long before a planet is even fully formed. What other biological building blocks are waiting to be discovered in those silent, frozen clouds? These complex molecules drifting in space point to a hidden signature written in infrared light. Across the galaxy, telescopes detect a set of faint, glowing bands that have become a universal fingerprint. They come from a family of molecules so widespread they are considered a fundamental component of the cosmic dust itself. These are the polycyclic aromatic hydrocarbons. That is a complex name for what are essentially flat, chicken wire-like molecules made of rings of carbon and hydrogen. You encounter them in everyday life. They are the soot from a candle flame, the char on a piece of grilled food, the byproducts of combustion. And yet, out in the cold vacuum between stars, they are everywhere. Their infrared glow paints the spiral arms of distant galaxies and fills our own Milky Way. They account for a significant portion of all the carbon in the galaxy, a staggering thought when you consider their size. But here lies the enigma. While we know the general class of molecule, we do not know the exact identities of the players, which specific polycyclic aromatic hydrocarbon molecules are out there. How many rings do they have? How are they oriented? We detect their collective choir, but we cannot pick out any single voice. Their formation is another puzzle. On Earth, they are made in hot, energetic processes like fires. In space, they are found in some of the coldest, most diffuse regions imaginable. So how do they get there? One theory suggests they are built up atom by atom on those frigid dust grains, a slow chemical knitting in the dark. Another proposes they are shattered fragments of larger carbon grains, broken apart by the very starlight that makes them glow. Their destruction is equally mysterious. They are surprisingly resilient, but under the barrage of ultraviolet radiation near hot stars, they can be broken down or transformed. This cycle of formation and destruction is a critical part of the interstellar medium's energy balance. These tiny molecules are extraordinarily efficient at absorbing a single photon of starlight. They vibrate with that energy and then re-release it as infrared heat. In doing so, they act as a universal coolant, helping giant molecular clouds shed energy so they can collapse to form new stars. They are both a product of stars and a midwife for new ones. Most intriguingly, their complex ringed structures make them perfect candidates as stepping stones. With their flat, stable surfaces, they could act as platforms where other atoms can dock and react, potentially building up toward the even larger prebiotic molecules we find in clouds. They may be the missing link between simple carbon atoms and the sugars and acids of interstellar chemistry. So the next time you see the soft glow of a distant nebula in an astronomical image, remember, a portion of that gentle light is the warm infrared hum of countless trillions of these carbon rings, a fundamental yet mysterious fabric of the galaxy, quietly orchestrating the birth of stars and perhaps the chemistry of life. Yet for all the molecules and dust we can detect, the interstellar medium holds a secret so vast it challenges our senses of the universe itself. We are missing matter, and not the dark kind. This is about the ordinary stuff, the protons and neutrons that make up stars, planets, and us. According to our best models of the Big Bang, we can calculate precisely how much of this normal matter, called baryonic matter, should exist in the universe. When we add up everything we can see, all the stars, galaxies, and the cool gas clouds, we come up short. A staggering 30 to 40% of the ordinary matter in our cosmic neighborhood is simply unaccounted for. It is the missing baryon problem, and the leading suspect for its hiding place is right here in our own galactic backyard, woven into the very fabric of the interstellar medium. Where could such an immense amount of material possibly be hiding without us seeing it? The answer lies in a state of matter so diffuse and so energetic that it has eluded our telescopes for decades. Astronomers call it the warm-hot intergalactic medium, But a key part of this mystery exists closer to home, in the circumgalactic medium surrounding our Milky Way and even within the local bubble, the vast cavity of hot gas in which our solar system floats. Imagine trying to see a wisp of steam in a darkened room using only a flashlight. That has been our challenge. This missing matter is not in cold, dense clouds that block starlight. It is believed to be a thin, superheated plasma, a gas so hot it glows not in visible light, but in far ultraviolet and soft X-rays, and so spread out that a cubic meter of it might contain only a few particles. To find it, astronomers have become cosmic detectives using indirect techniques. One powerful method is absorption line studies. Just as the diffuse interstellar bans fingerprint molecules, we can use the light from distant quasars, the brilliant beacons at the hearts of ancient galaxies, as a backlight. As that light journeys through the halos of galaxies and the spaces between them, the hot, ionized gas in the warm hot medium strips electrons from atoms like oxygen and nitrogen. These ionized atoms absorb very specific high-energy wavelengths in the quasar's light. By finding these faint, telltale dips in the ultraviolet spectrum, we can map the presence and properties of this invisible gas. The other key tool is X-ray observatories like Chandra. They search for the faint, diffuse glow this million-degree plasma should emit. It is an incredibly difficult signal to tease out from the cosmic background, like listening for a single instrument in a symphony played from another city. Recent observations are starting to pay off, finding tentative filaments of this hot gas in the vast web-connecting galaxy clusters. The implication is profound. The interstellar medium is not an isolated phenomenon. It is the denser part of a continuous, dynamic atmosphere that envelopes entire galaxies and fills the cosmic web. The local bubble, likely carved out by ancient supernovae, is filled with this very hot, tenuous gas. We are swimming in the solution to the missing baryon problem. This hidden ocean of plasma is the universe's hidden skeleton, a reservoir of ordinary matter that has been there all along, just too faint and too energetic for our eyes to see. It means the empty spaces of our galaxy are not empty at all, but brimming with a faint, hot breath that holds the final pieces of our universal inventory. What other secrets are written in the X-ray whispers of this elusive, scorching sea? These vast reservoirs of complex chemistry are not formless blobs. They possess a hidden architecture, a ghostly skeleton that defies simple explanation. When we look at the birthplaces of stars, the great molecular clouds like Orion or Taurus, the most striking feature is not their size but their intricate texture. They are not smooth, they are a chaotic, tangled web of filaments. Images from observatories like Herschel reveal this in breathtaking detail. The darkness is threaded with countless rivers of denser gas and dust, twisting and braiding into a cosmic labyrinth. Some filaments stretch for dozens of light years, yet are only a fraction of that in width, like impossibly long, dark threads suspended in the void. This universal filamentary structure is the first clue to a deeper mystery. What sculpts these clouds into such specific shapes, and what determines which threads will eventually give birth to stars? The answer lies in a fierce, invisible battle between three titanic forces: gravity, turbulence, and magnetism. Gravity is the great unifier, the force that wants to pull everything together into a single, dense point. Left unchecked, it would cause these massive clouds to collapse into stars in a cosmic blink, but they do not. They persist for millions of years, slowly simmering. Something is holding them up, providing support against their own weight. For a long time, astronomers thought magnetic fields were the primary backbone. Imagine the cloud threaded with invisible lines of magnetic force, like a complex network of elastic bands. The charged particles in the gas would be forced to spiral along these lines, resisting any motion that tries to pull them across. This magnetic pressure could, in theory, prop up a cloud for eons. Yet observations suggest the fields within these clouds are often incredibly weak and tangled, perhaps too weak to be the sole support. This brings us to the second contender, supersonic turbulence. The interior of a molecular cloud is not a serene place. It is a roaring, chaotic storm. Motions within the gas rush at speeds far greater than the speed of sound, creating a network of shocks and eddies that crisscross the cloud. This constant churning acts like a powerful, chaotic pressure, stirring the pot and preventing any one region from settling down long enough to feel gravity's full pull. Think of it as trying to build a sandcastle in the middle of a hurricane. The wind keeps knocking the grains apart, but turbulence has a paradoxical nature. While it supports the cloud on large scales, it also creates the very conditions for collapse on smaller ones. Where two turbulent flows collide head-on, they can compress the gas into a knot dense enough for gravity to finally take over. So the cloud is in a precarious balance, a structure born from chaos, where support and destruction are two sides of the same violent coin. The ultimate mystery is the trigger. What tips the balance in one particular filament or not, dooming it to become a star? It could be the shock wave from a distant supernova, slamming into the cloud like a cosmic tsunami. It could be the collision of two clouds or the gradual erosion of the magnetic field as particles slowly slip across the lines. The James Webb Space Telescope is now peering into the hearts of these filaments, searching for the densest cores where the battle is finally being lost to gravity. Within those sheltered, dusty cocoons, the first flickers of new suns are igniting. The structure of the cloud, therefore, is not a static stage. It is a frozen snapshot of an eternal war, a battlefield where the laws of physics decide where and when the next lights in the galaxy will be born. What does this delicate balance tell us about our own sun's long-forgotten cradle? The chaotic battle within star-forming clouds points to a silent, invisible commander. Magnetic fields permeate the interstellar medium, a ghostly lattice of force that guides the flow of matter itself. We cannot see them directly, but their influence is everywhere, from the graceful spiral arms of galaxies to the alignment of the tiniest dust grains. Their true power, however, remains one of the most contentious mysteries in astrophysics. Do these magnetic fields act as a rigid skeleton, fiercely resisting the collapse of gas into stars? Or do they serve as cosmic highways, gently channeling material along their lines into the dense cores where stars are born? The answer is frustratingly elusive, because measuring something you cannot see in an environment you cannot touch is an extraordinary challenge. To detect these fields, astronomers rely on clever tricks written into the light and the dust. One method probes the atoms themselves. When a cloud is permeated by a magnetic field, the energy levels of atoms like hydrogen shift in a process called Zeeman splitting. It is a tiny effect, like a faint double image in the radio waves emitted by the gas. Measuring that minuscule split tells us the field's strength, but it is like trying to hear a whisper in a hurricane. It only works in the densest, most active regions. For mapping the field's direction across vast stretches of sky, we look to the dust. Those microscopic grains are not spherical. They are thought to be elongated, like tiny cosmic needles. As they drift through space, the weak interstellar magnetic field causes them to spin, aligning their long axes perpendicular to the field lines. When starlight passes through a cloud filled with these aligned grains, it becomes polarized. Its light waves oscillate in a preferred direction. By measuring this polarization from missions like the Planck satellite, we can trace the field's orientation. The resulting maps are breathtaking. They show magnetic fields flowing along the edges of giant bubbles, wrapping around molecular clouds and creating a vast, swirling tapestry that connects the entire galaxy. The patterns are clear, but their ultimate effect is not. In some clouds, the field appears strong and orderly, potentially providing enough pressure to hold back gravity. In others, it looks tangled and weak, overwhelmed by turbulent motions. The emerging picture is one of a dynamic partnership. magnetic fields may initially provide support, like the scaffolding on a building. But as a cloud fragment begins to collapse, the field lines can become pinched and distorted. They might not stop the collapse entirely, but they can slow it down, regulating the birth of a star and perhaps even directing the spin of the resulting protoplanetary disk. They could be the reason stars are not born all at once in a frantic rush, but in a slow, orchestrated procession. This invisible architecture, woven through the darkness, may be the silent architect that decides not just where a star forms, but what kind of star it will become. Magnetic fields provide a ghostly scaffold, but the real chaos within the clouds comes from a relentless, unseen storm. The interstellar medium is not a placid sea. It is a churning, supersonic maelstrom where gas moves at speeds exceeding 100,000 miles per hour, far faster than the speed of sound in that thin medium. This is not gentle stirring. This is interstellar turbulence, and it is the dominant force sculpting the galaxy's structure on almost every scale. The great mystery is not its existence, but its origin. What cosmic engines are powerful enough to keep this entire galactic ocean in a state of perpetual, violent motion? The prime suspects are the most energetic events in the galaxy. When a massive star ends its life in a supernova explosion, it does more than create dust and scatter elements. It detonates with the force of 1 billion suns, launching a spherical shockwave that plows into the surrounding gas for thousands of light years. This is like a titanic boulder dropped into a pond, sending ripples of compression and chaos through the interstellar medium. Stellar winds from young, hot stars act as relentless jets, carving out vast bubbles and pouring energy into their surroundings. Even the slow, grand rotation of the Milky Way itself shears and stretches the gas, injecting a baseline level of disorder. Yet, when astronomers try to balance the energy budget, a puzzle emerges. The amount of turbulence we observe seems to demand a constant, widespread source of power. Do supernovae occur frequently enough and in the right places to sustain the chaos we see in quiet, distant clouds? Are there other, more subtle contributors, like the collective effect of countless smaller stellar outflows, or even the gravitational pull of the galaxy's unseen dark matter halo? We can see the effects of turbulence everywhere. It is the reason molecular clouds have that intricate fractal filamentary structure rather than being simple collapsing spheres. The turbulent flows collide, creating networks of shocks that compress gas into the dense knots where stars can eventually form. In this way, turbulence is a paradoxical architect. On the grand scale, its violent pressure supports entire clouds against gravity's relentless pull, preventing a catastrophic, galaxy-wide burst of star formation. But on local scales, it creates the very overdensities where gravity finally wins. It simultaneously regulates the birth rate of stars and determines their birthplaces. Furthermore, this chaos is a primary heating source. The supersonic motions eventually dissipate like ocean waves crashing on a shore, and that energy heats the surrounding gas, preventing it from cooling into a simple, uniform freeze. The problem is we do not fully understand how this energy cascades down from the colossal scale of a supernova remnant to the tiny scales where it finally dissipates as heat. It is a cosmic chain of energy transfer we have yet to fully map, so the turbulence we observe is more than just chaos. It is the signature of the galaxy's violent heartbeat, a constantly refreshed storm that structures the cosmos, governs the pace of creation, and keeps the interstellar medium alive with motion. Without it, the galaxy would be a very different and far more static place. What other hidden engines might be stirring this eternal, supersonic soup? This relentless turbulence is a source of heat, but it is only one player in a delicate cosmic thermostat. The interstellar medium exists in a state of profound thermal disequilibrium. In the very same region of space, you can find gas so cold it approaches absolute zero, mere degrees from the complete absence of heat, and plasma so hot it glows with X-rays. How can these extremes coexist side by side without instantly averaging out? The answer is a complex, dynamic balance between heating and cooling, a puzzle that dictates the very structure of the galactic ecosystem. For the interstellar medium to maintain its distinct phases, the cold molecular clouds, the warm neutral hydrogen, and the hot ionized bubbles, the energy books must be meticulously balanced. The heating mechanisms are as varied as they are subtle. Cosmic rays, those high-speed atomic nuclei racing across the galaxy, are a major contributor. They do not heat the gas like a flame. Instead, they slam into atoms, knocking electrons loose in a process called ionization. The energy from that collision gets distributed as motion, warming the gas from within. Then there is the photoelectric effect, but on a cosmic scale. Starlight, particularly ultraviolet light, strikes those ubiquitous dust grains. The grains absorb the energy and eject electrons, which then zip through the surrounding gas, colliding with atoms and transferring their kinetic energy as heat. It is a process where dust, ironically, helps warm the very space it obscures. And of course, the dissipation of that supersonic turbulence we discussed acts as a final, widespread heating source, like friction in a galactic engine. But for every source of heat, there is an equally efficient cosmic coolant. This is where the chemistry of space becomes its own air conditioning system. Atoms and molecules are brilliant at shedding energy. When an atom like carbon or oxygen is excited by a collision or absorbed photon, it does not stay excited for long. It relaxes back to its normal state by emitting a photon of very specific light, often in the infrared or radio part of the spectrum. This photon simply flies away into the void, carrying the thermal energy of the gas with it. In the dense, cold cores of molecular clouds, more complex molecules like carbon monoxide become the primary coolant. They rotate and vibrate, emitting millimeter-wave radiation that escapes easily, allowing the cloud's core to sink to temperatures only a few tens of degrees above absolute zero. This efficient cooling is what permits gravity to finally overcome pressure, triggering the collapse to form stars. The mystery for astronomers is modeling this balance with precision. The rates of heating and cooling depend on a dizzying array of factors: the local density, the strength of the starlight, the abundance of dust and heavy elements, the intensity of the magnetic field. A slight shift in one variable can tip a region from a warm, diffuse haze into a cold, contracting cloud, or blast it apart into a hot, expanding bubble. This thermal ballet explains the patchwork structure we observe. It is why we see sharp boundaries between dark, cold filaments and glowing, hot cavities. The entire life cycle of the interstellar medium, from quiet cloud to stellar nursery to supernova remnant, is governed by this ceaseless exchange of energy. If the cooling were too efficient, the entire galaxy might freeze into a monolithic, star-forming collapse. If heating dominated, the gas would remain too hot and diffuse to ever coalesce. We exist in a galaxy poised between these extremes, its beauty and structure born from a thermal tightrope walk we are only beginning to map. This delicate thermal balance reveals a hidden ocean of light. Spanning the vast spaces between the stars and even reaching high above the galactic plane, there exists an immense, ghostly realm of ionized hydrogen. Astronomers call it the warm ionized medium. It is not the blistering plasma of a supernova remnant, nor the cold heart of a molecular cloud. It is a pervasive, lukewarm fog, a state of matter so tenuous that a coffee mug's worth of it would contain barely a few dozen atoms. Yet, because it fills such an enormous volume, it represents one of the single largest components of the entire interstellar medium by mass. We know it is there because of two faint signatures. The first is a specific rosy glow in the night sky, the emission line of hydrogen alpha light. This is the same glow that paints the great nebulae, but here it is not concentrated in beautiful clouds. It is a diffuse, almost imperceptible background haze, detectable only with sensitive instruments after subtracting the light of every star and known nebula. The second clue comes from the cosmic lighthouses known as pulsars. As their rapid clock-like radio pulses travel to Earth, they pass through this ionized fog. The free electrons within it scatter the radio waves very slightly, causing a subtle twinkling or scattering that tells us the density and turbulence of the gas along the line of sight. The existence of this medium is clear. Its origin, however, is a deep puzzle. What keeps this gas ionized so far from any obvious source of power? In a dense nebula, a single, hot, young O-type star provides more than enough ultraviolet radiation to strip electrons from hydrogen atoms. But the warm ionized medium is everywhere, even in the lonely voids far from such stellar power plants. The radiation from all the known hot stars in the galaxy, if it traveled in straight lines, simply could not reach and ionize all this volume. So the energy must be leaking somehow. One leading theory involves a galactic fountain effect, where supernova explosions loft hot gas high above the disk. As this gas rises and cools, it might mix turbulently with cooler material, creating interfaces where ionization can occur. Another idea points to the combined, faint ultraviolet glow from countless older, less massive stars, a kind of cosmic background radiation of starlight that slowly, cumulatively does the work. There are even suggestions that lower energy cosmic rays or the decay of certain dark matter particles could contribute. Whatever the source, it must be remarkably efficient and widespread, a gentle but persistent ionization drizzle falling across the entire galaxy. This makes the warm ionized medium a critical, yet poorly understood, part of the galactic ecosystem. It acts as a conductive bridge between the hot, coronal gas of the galactic halo and the cooler, denser material of the disk. It may help regulate the flow of energy and matter in and out of the star-forming regions below. Its very presence tells us that the galaxy is not a collection of isolated neighborhoods, but a fully connected electrical circuit, humming with a faint, ionized current. Solving this mystery means understanding how energy on the grandest scales is distributed and recycled. It is the search for the galaxy's hidden power grid, the faint glow that proves even the darkest voids are alive with subtle charge. That faint, ionized haze points to a relentless rain of invisible bullets. Deep within the warm ionized medium and throughout every corner of the interstellar sea, there exists a constant drizzle of atomic shrapnel moving at nearly the speed of light. These are galactic cosmic rays, and while the name suggests radiant beams, they are actually subatomic particles, mostly protons and atomic nuclei, hurtling through space with unimaginable energy. They are the most energetic particles in the galaxy, yet their origin story is a century-old detective case that remains frustratingly unsolved. We know they are there because we can detect them directly with instruments in space and even with ground-based observatories that catch the cascading showers they create when they strike our atmosphere. We can measure their energy and their composition, but tracing them back to their source is like trying to find which particular raindrop in a hurricane came from which cloud. The leading theory, one that has held for decades, points to the aftermath of stellar cataclysms. When a massive star explodes as a supernova, the expanding shockwave is a natural particle accelerator of cosmic proportions. The chaotic, magnetized shell of the remnant can trap charged particles, forcing them to bounce back and forth across the shock front. With each crossing, they gain a little more speed, like a surfer being pushed repeatedly by a wave, until they are ejected into the galaxy with a significant fraction of light speed. This process, called diffusive shock acceleration, is elegant and theoretically sound. Supernova remnants should be cosmic ray factories. The problem is definitive proof has been maddeningly elusive. We have not yet convincingly detected the telltale sign, a specific pattern of high-energy gamma rays that would be the smoking gun proving protons are being accelerated to these extreme energies within a remnant. We see gamma rays, but they could be produced by electrons, not the atomic nuclei that make up the bulk of cosmic rays. It is a case of strong circumstantial evidence without a confession. This leads to other, more exotic suspects. Could the turbulent winds from entire clusters of massive stars act as a collective accelerator? Might the environment around the supermassive black hole at our galaxy's center be hurling out ultra-high-energy particles? The mystery of their acceleration is matched by the puzzle of their journey. Once launched, these particles do not travel in straight lines. They spiral along the tangled magnetic field lines that weave through the interstellar medium. Their path is a chaotic, random walk, a drunkard stumble across the galaxy that can last for millions of years before they eventually escape into intergalactic space or collide with something. During this epic journey, they play a role far out of proportion to their minuscule size. They are a primary ionizer of the interstellar gas, particularly in the dense, dark clouds where starlight cannot penetrate. A single high-energy cosmic ray can knock an electron free from a hydrogen molecule, creating the ionized chemistry that allows complex molecules to form. They are the initiators, the spark in the dark that gets the interstellar chemical engine running. Yet for all their creative power, they also represent one of the most formidable barriers to human exploration beyond Earth's protective magnetic field. For astronauts on a journey to Mars or living on a lunar base, this constant penetrating rain of high-energy nuclei poses a severe radiation hazard. It can damage electronics, break down DNA, and increase long-term cancer risks. Shielding against it is immensely difficult, as these particles can smash through conventional materials, creating secondary showers of radiation inside a spacecraft or habitat. Understanding cosmic rays is therefore not just an academic puzzle. It is key to mapping the galaxy's hidden energy budget, to deciphering the chemistry of life's building blocks, and to one day safely navigating the ocean between the stars. We are, in a very real sense, trying to understand the weather in the medium we must one day sail. This chaotic storm of gas and magnetism sets the stage for the most critical transformation of all. Within the tangled filaments of a molecular cloud, something remarkable happens. Tiny pockets of gas begin to pull away from the chaos, growing denser and colder than their surroundings. These are prestellar cores, the cosmic droplets from which stars will eventually condense. Their formation is the pivotal mystery, the moment when a diffuse cloud fragment crosses an invisible threshold and becomes a star's cradle. How does a specific knot of gas, adrift in a supersonic maelstrom, manage to shield itself, grow quiet, and begin its fatal fall toward becoming a sun? The forces at play are a delicate trio. First, thermal pressure, the outward push of warm gas molecules, is the most straightforward opponent of collapse. But in these cores, the cooling is so incredibly efficient. Molecules like carbon monoxide radiate away the heat, allowing the temperature to plummet to just 10 degrees above absolute zero. With the thermal pressure dropping, gravity gains a powerful advantage. Second, there is the possible support from magnetic fields. If the field lines are strong enough and threaded through the core, they can act like a cage of elastic bands, providing magnetic pressure that resists the inward crush. The key question is whether particles can slowly drift across these field lines, a process called ambipolar diffusion, which would eventually undermine this support over hundreds of thousands of years. And third, there is the decay of that supersonic turbulence. Within a small region, the chaotic motions can dissipate like a local storm passing. When this happens, the turbulent pressure that was propping up the gas vanishes and gravity finds its opening. The exact trigger for any given core is likely a unique combination of these factors, a chance confluence where cooling wins, turbulence calms, and magnetic support slowly leaks away. What emerges from this process is a pattern that echoes throughout the cosmos. Astronomers measure the masses of these prestellar cores, creating what they call the core mass function. It is a census of these star-forming droplets. Astonishingly, this distribution of core masses looks almost identical to the initial mass function of stars themselves. There are many more low-mass cores than high-mass ones. This is a profound clue. It suggests that the mass of a star is largely determined at this very early stage, set by the amount of gas that gathers into a coherent droplet before collapse begins in earnest. It implies that the chaotic, stormy environment of the parent cloud is not random in its outcome, but follows a hidden statistical rule. The physics of turbulence and gravity conspire to fragment the cloud into a predictable spectrum of pieces, from tiny stellar seeds that may become red dwarfs to massive clumps destined for brilliant, short lives. So when we look at the variety of stars in our night sky, the faint red ones and the brilliant blue giants, we are seeing the final product of a selection process that began in the dark, long before nuclear fusion ever ignited. The mystery of the core is the mystery of stellar destiny, written in cold gas and silent magnetic fields, waiting for gravity to turn the page. These stellar cradles are among the coldest places in the universe. Within the deepest, darkest hearts of molecular clouds, starlight cannot penetrate. Temperatures hover just a few degrees above absolute zero, and the density, while greater than the surrounding void, is still a vacuum far emptier than anything we can create on Earth. It is here, in this frigid, lightless environment, that the interstellar medium performs its most astonishing chemical magic. Shielded from the destructive power of ultraviolet radiation, atoms and simple molecules meet on the only solid surfaces available, the microscopic dust grains. These grains become cosmic ice rinks where chemistry defies our everyday expectations. The first step is the formation of a frosty mantle. Atoms like oxygen, nitrogen, and carbon, along with simple molecules such as hydrogen and carbon monoxide, drift through the cloud. When they collide with a dust grain in this profound cold, they do not bounce off. They stick, frozen in place by a phenomenon called physisorption. Over millennia, these atoms build up in layers, creating an icy coating of frozen water, carbon dioxide, ammonia, and methanol. This ice is not pure. It is a messy, porous mixture, a primordial slush. On this frozen stage, the real chemistry begins. Two hydrogen atoms, for instance, might land near each other. They are so cold they have almost no thermal energy to react. Yet, observations tell us molecular hydrogen forms abundantly in these clouds. How? The answer involves a bizarre quantum mechanical effect called tunneling. In our macroscopic world, a ball needs enough energy to roll over a hill. At quantum scales, a particle like a hydrogen atom can sometimes simply appear on the other side of an energy barrier, as if the hill had a secret tunnel. This allows reactions to proceed at temperatures where classical chemistry says they should be utterly frozen. Laboratory experiments here on Earth strive to recreate these conditions. Scientists use ultra-high vacuum chambers cooled to within a fraction of a degree of absolute zero. They introduce gases to form ices on a simulated dust surface, then zap them with radiation or simply wait, using sensitive instruments to detect what molecules form. These experiments have shown that complex organic molecules, like the sugar glycolaldehyde or the amino acid precursor glycine, can indeed be forged on icy grains. The process is achingly slow by human standards, but given cosmic timescales of millions of years, it becomes a factory of complexity. The challenge for astrochemists is monumental. Modeling this chemistry requires accounting for thousands of possible reactions on a diverse array of grain surfaces, all at temperatures where quantum weirdness reigns. Every new molecule detected in a dark cloud, like Sagittarius B2, is a clue, a piece of a formula written in the dark. This means the fundamental ingredients for water ice, for simple sugars, and for the precursors to life's machinery are not planetary inventions. They are universal products manufactured in the silent, frozen darkness long before a star begins to shine. What other recipes are being quietly assembled in the galaxy's coldest, darkest kitchens? The chemistry of ices hints at a profound journey, one that every microscopic dust grain must undertake. These are not permanent fixtures of the cosmos. Each speck is a transient voyager on an epic circuit, a cycle of creation, transformation, and destruction that we call the life cycle of interstellar dust. It begins, as all things do, with the death of a star. In the extended, gentle winds blowing from a cool, aging red giant, atoms like silicon, carbon, and iron flow outward into space. As this expanding shell of gas cools, these atoms find each other and condense directly from a vapor into solid grains. It is a slow cosmic snowfall, building up soot-like carbon particles and sand-like silicates over thousands of years. A more violent birth occurs in the furious ejecta of a supernova. The titanic explosion creates a rich soup of heavy elements, and within the rapidly cooling shockwave itself, conditions are just right for dust to nucleate in a frantic instant. We have even seen this in the remnants of supernova like Cassiopeia A, where infrared telescopes detect vast quantities of freshly forged dust. So the journey starts with a gift from the stars, a legacy of elements cast into the void. But this newborn dust does not get to rest. It is immediately plunged into the harsh reality of the interstellar medium. For millions of years, it drifts through a gauntlet of dangers. It is bombarded by ultraviolet photons from hot stars and slammed by cosmic rays. Individual atoms can be knocked right off its surface in a process called sputtering, slowly eroding the grain away. In the turbulent flows between stars, grains collide. Sometimes these collisions are gentle. The grains stick together in a process called coagulation, building up larger, fluffy aggregates that are the first steps toward pebbles and planetesimals. Other collisions are violent at supersonic speeds. They shatter the grains into smaller fragments, replenishing the population of tiny specks and changing the overall size distribution of dust in the galaxy. A single grain might also find itself swept up into a dense molecular cloud, where it acquires a thick mantle of ices, only to have that mantle blasted away when a new star ignites nearby. It is a life of constant processing, where a grain's composition, size, and shape are remade by its environment. Ultimately, every grain's journey must end. There are two primary fates, and both are dramatic. The first is complete destruction. If a dust grain is caught in the powerful shockwave of a supernova, perhaps even one that formed at the raging front of hot plasma can vaporize it entirely, returning its atoms to the gaseous state to begin the cycle again. The second fate is one of glorious incorporation. Within a protoplanetary disk swirling around a young star, dust grains settle into the midplane. They collide, stick, and grow step by step from microscopic specks into rocks, then asteroids, comets, and finally, the very bedrock of planets. Every mountain on Earth, every grain of sand on a distant exoworld, began as a nameless mote adrift between the stars. This raises a critical, unresolved question for astronomers. Is the galactic dust budget balanced? We can estimate the sources, the rate at which stars are producing new dust. We can also estimate the sinks, the rates of destruction in shocks and locking away in planets. The numbers, frustratingly, do not quite add up. Observations suggest supernova should be efficient destroyers of dust, yet we see plenty of dust in young galaxies not long after the Big Bang. Are our models of destruction wrong, or are there hidden, prolific sources of dust we have not yet accounted for? The life cycle is thus more than a story. It is an accounting problem on a galactic scale, a puzzle of cosmic conservation that tells us whether the universe is a net producer or a relentless recycler of the solid seeds from which worlds are born. Our own solar system is not a lonely ship sailing through a uniform sea. We are floating inside a specific, remarkable structure within the interstellar medium, a vast cavity called the local bubble. This is not a metaphor, it is a real physical cavity in the galaxy's disk, roughly 300 light-years across, shaped like a peanut or an hourglass. Inside this bubble, the gas is extraordinarily hot and incredibly thin, a plasma of about 1,000,000 degrees, but so diffuse that it contains only about 1 atom for every 10 cubic centimeters. For comparison, the air you breathe has about 25 billion molecules in the same tiny space. We live in a near-perfect vacuum, but one that is scorching hot. How did we get here? The walls of our celestial home were forged by violence. Between 10 and 20 million years ago, not far from our present location, a series of massive stars were born in a loose cluster. These stars lived fast and died young. One by one, they exploded as supernovae. Each detonation sent a blistering shockwave plowing into the surrounding interstellar gas, sweeping it up, heating it to extreme temperatures and pushing it outward. Think of it as a series of cosmic snowplows, clearing out the dense, cold material and leaving behind this enormous, hot cavity. The expanding shells of these remnants eventually merged, creating the single, giant bubble we inhabit today. Its inner surface, which we can map by the glowing X-rays it emits, is still slowly expanding into the surrounding galactic disk. This means our entire neighborhood, the region containing the closest stars like Alpha Centauri and Sirius, shares this unique historical address. We are all children of those ancient stellar explosions, living in their still warm aftermath. Yet within this grand hot bubble, there is a curious and intimate detail. Our solar system is currently passing through a small, wispy cloud of slightly cooler, denser gas embedded within the local bubble. Astronomers call it the local interstellar cloud, or sometimes, with charming simplicity, the local fluff. It is about 30 light-years across, and while still a vacuum by earthly standards, it is about 10 times denser than the surrounding bubble gas and much cooler, at a mere 7,000 degrees. We have been moving through this cloud for perhaps the last 50,000 years and will emerge from it in another 10,000 or so. How do we know we are inside it? The telltale signs are in the neutral helium and hydrogen atoms that stream into our solar system from this specific direction, detected by spacecraft like Voyager and IBEX. This cloud is not strong enough to compress the sun's magnetic field, but it does gently shape the outer reaches of our heliosphere, the protective bubble of solar wind that surrounds us. The existence of the local fluff highlights a crucial truth. The interstellar medium is not a smooth gradient. It is a fantastically patchy and clumpy foam, where hot bubbles and cool clouds jostle against each other in a complex, layered structure. Our place in this ecosystem is not static. We are transient visitors in a small cloud, which is itself a fleeting texture inside a giant, aging cavity. This dynamic reality forces us to ask a profound question about our own history. As the solar system orbits the galaxy, it has undoubtedly passed through many different interstellar environments over its 4.5 billion-year life. What happens when we enter a dense molecular cloud or a region of intense radiation? Could such passages have affected Earth's climate or the flux of cosmic rays reaching our planet, potentially influencing the course of life itself? Our address within the interstellar medium is temporary, a single frame in a long cosmic film, reminding us that the space between the stars is alive with structure and change. The local fluff is a gentle wisp, but far above the galactic plane, the sky is falling. Racing toward the disk of the Milky Way at speeds exceeding 100 kilometers per second are vast, dark structures of cold, neutral hydrogen. We call them high-velocity clouds, and they are one of the most dramatic and mysterious forms of accretion in our galaxy. Imagine colossal, shadowy islands of gas, some spanning thousands of light years, plunging silently from the galactic halo toward the starry disk below. They are not stars, they emit no visible light of their own. We only know they are there because of the 21-centimeter radio line, the faint but unmistakable whisper of cold hydrogen atoms. Their motion is the puzzle. They are moving far too fast to be simply orbiting within the galaxy's disk. They are incoming, a relentless high-speed rain of raw material. So where is this gas coming from, and what force is hurling it toward us? The leading theories paint a picture of a dynamic, even violent, galactic ecosystem. One compelling idea is that these clouds are the tidal debris of cosmic cannibalism. As the Milky Way's immense gravity tears apart smaller, dwarf galaxy satellites, it can strip away their gas, stretching it into long, streaming filaments that eventually condense into these falling clouds. Another prime suspect is the Magellanic Stream, a gigantic ribbon of gas torn from our neighboring large and small Magellanic Clouds as they orbit our galaxy. Parts of this stream could be breaking up and accelerating toward the disk, appearing to us as individual high-velocity clouds. A third possibility is more subtle, yet equally profound. This gas might not be coming from outside at all, but condensing out of the galaxy's own hot corona, the immense million-degree atmosphere of plasma that surrounds the Milky Way. As this superheated gas cools in localized pockets, it could precipitate into cold, dense clouds that then fall inward, a form of galactic rainfall. Determining which explanation is correct is maddeningly difficult because we lack one crucial piece of information: precise distance. Without knowing exactly how far away a high-velocity cloud is, we cannot calculate its true size or mass. Is it a nearby, small cloud or a distant, gargantuan one? Astronomers use clever tricks to estimate distances, like looking for the faint absorption features of the cloud in the light of distant stars, which tells us the cloud lies in front of those stars. But these background stars are sparse, leaving vast gaps in our three-dimensional map. Their role, however, is potentially transformative. These clouds represent a fresh infusion of fuel, a delivery of pristine hydrogen gas that has not yet been cycled through generations of stars. When they eventually crash into the galactic disk, perhaps in another 50 million years, the shock of impact could compress the gas, triggering new waves of star formation. They are the galaxy's future, falling from the darkness above. The mystery of their origin is therefore a question about the Milky Way's past and its future. Are we watching the final breaths of devoured galaxies, or the slow, steady respiration of our galaxy's own vast atmosphere? This silent rain from an invisible sky holds the answer. That silent rain of gas from the halo is one form of invisible light, but it is not the only one. The galaxy hums with a background whisper we cannot hear with our ears, a faint, anomalous microwave emission that blankets the sky. For decades, astronomers mapping the cosmic microwave background, the afterglow of the Big Bang, kept finding an irritating foreground static. It was a pervasive, diffuse hiss that refused to go away, and it was clearly coming from within our own galaxy. This was not the radio glow of synchrotron radiation from cosmic electrons, nor the thermal emission from warm dust. It was something new, something strange, and it became known as the anomalous microwave emission. The key clue to its origin was its correlation with interstellar dust. Wherever there were dense clouds of those microscopic grains, this particular microwave hum was stronger. Yet the standard models of dust emission could not explain it. Dust heated by starlight should glow in the infrared. This was a signal in the microwave, a much lower energy band. So what process could make cold dust grains sing in microwaves? The leading and quite beautiful theory involves rotation. Imagine a dust grain, but not the kind we have discussed before. These would be tiny, perhaps only a nanometer in size, mere clusters of a few hundred atoms. They are so small they are essentially large molecules, and they would be asymmetric, not perfectly round. In the harsh environment of space, these nanograins can become electrically charged, perhaps by losing an electron to a cosmic ray or by the photoelectric effect. Once charged, they become subject to the galaxy's magnetic fields. The interaction is like a tiny, cosmic electric motor. The magnetic field exerts a torque on the charged grain, causing it to spin, and spin incredibly fast, billions of rotations per second. And here is where physics performs its magic. Any rotating, charged object is a miniature radio transmitter. As these frenetically spinning nanograins tumble through space, they emit radiation right in the microwave part of the spectrum. This phenomenon is called spinning dust emission, and it elegantly explains the observed correlation and the spectrum of the anomalous signal, but the mystery is far from solved. The debate now centers on the exact identity of these spinning emitters. What are they made of? Are they tiny flakes of carbon, perhaps the same polycyclic aromatic hydrocarbons we see in the infrared? Or could they be minuscule silicate particles or even clusters of diamond-like carbon? Each material would have slightly different electrical properties affecting how it charges, spins, and ultimately, the precise frequency of its microwave hum. Observations from advanced radio telescopes are trying to pin down these subtle spectral details, listening for the specific note in the cosmic static that reveals the grain's composition. Furthermore, the emission itself is unusually anomalous because it requires a very specific environment. The spinning dust model predicts the signal should be strongest in regions that are not too hot and not too cold, the warm, neutral parts of the interstellar medium where grains can get charged but not destroyed. This makes the anomalous microwave emission a sensitive probe of conditions we cannot easily see, a thermometer and a density gauge written in microwaves. So this pervasive hiss is more than just background noise. It is the collective drone of countless trillions of microscopic cosmic tops spinning in the magnetic winds of the galaxy. Their song tells us that the dust between the stars is not just a passive curtain or a chemical laboratory, but a dynamic, electrically active component of the interstellar sea, humming with a hidden energy all its own. What other secrets might be encoded in the galaxy's faint microwave whisper? Those spinning nanograins humming with microwave energy point to a deeper census problem in the galactic dust population. When astronomers carefully measure the sizes of dust grains drifting through the diffuse interstellar medium, they find a glaring absence. The very smallest grains, the ones just nanometers across, seem to be missing in action. This is not a trivial accounting error. The size distribution of dust is a fundamental property, a fingerprint of its entire life cycle from creation to destruction. The fact that this fingerprint appears to lack the tiniest fingers is a clue that something violent is systematically erasing them from the cosmic record. Where have all the small grains gone? The interstellar medium should be littered with them. They are the natural byproducts of both dust formation in stellar winds and the shattering collisions of larger grains in turbulent gas. We see evidence for their existence in specific environments, like the spinning dust emission, and in the ultraviolet extinction curves that show how starlight is dimmed and reddened. Yet, when we take a broad survey of the general, diffuse space between stars, their numbers do not add up. They are far fewer than our models predict. Two prime suspects stand accused of this cosmic vanishing act, and both are agents of immense power. The first is the relentless glare of interstellar ultraviolet radiation. In the diffuse medium, far from the protective cloak of dense clouds, dust grains are bathed in the combined starlight of the galaxy. For a very small grain, perhaps only a few hundred atoms in size, absorbing a single ultraviolet photon is a catastrophic event. The energy delivered is so concentrated that it can violently heat the entire grain to temperatures of hundreds of degrees in an instant. This thermal spike can be enough to break molecular bonds and literally evaporate atoms right off the surface, a process called photodesorption. Over time, this persistent microscopic sandblasting could erode the smallest grains down to nothing or shatter them into individual atoms. The second, and perhaps more dramatic, suspect is the shockwave from a supernova explosion. As that titanic wall of plasma plows through the interstellar medium at thousands of kilometers per second, It creates a hostile environment of extreme temperatures and pressures. A tiny dust grain caught in this maelstrom faces multiple threats: sputtering, where high-energy atoms in the shock strip it away layer by layer; vaporization, if the grain is heated past its sublimation point; and shattering from catastrophic collisions with other grains accelerated by the shock. Supernova shocks are thought to be the primary destroyers of dust in the galaxy, but the mystery lies in the efficiency. Are they 100% efficient, wiping the slate completely clean in their path? Or do some hardy, small grains survive, perhaps by being flung ahead of the shock or embedded in denser, protected clumps? The timescales are equally puzzling. If small grains are being produced constantly by collisions and destroyed just as quickly by these processes, we are seeing a snapshot of a dynamic equilibrium. But does the rate of destruction outpace the rate of production? The answer has profound implications. The dust-size distribution directly shapes the interstellar extinction curve, the precise map of how much starlight is blocked at each color. A lack of small grains would mean less blue light is scattered, changing the very reddening effect we use to measure distances across the galaxy. It also affects the chemistry. Small grains have the largest surface area relative to their mass, making them the most active sites for molecule formation. If they are scarce in diffuse space, the chemical pathways to complexity might be very different there than in dense clouds. This disappearance is therefore a clue to the galaxy's violent weather patterns. It tells us that the calm, diffuse stretches between stars are not a refuge, but a proving ground where only the resilient survive. The smallest grains are the most vulnerable, the first to fall in the endless interstellar war between creation and destruction. Their absence is a silent testimony to the power that shapes the medium we see. What other delicate structures might be invisibly erased by the galaxy's constant fury? The absence of small grains speaks to a universe of elemental balances, but one light element stubbornly refuses to balance at all. Among the very first atoms forged in the fiery minutes after the Big Bang were the lightest ones: hydrogen, helium, and a tiny trace of lithium. According to our exquisitely precise models of Big Bang nucleosynthesis, we can calculate exactly how much of each should have been created. For hydrogen and helium, the predictions match the observed abundances in the oldest stars almost perfectly. But for lithium-7, the most common stable isotope, something is profoundly wrong. The oldest, most pristine stars in our galaxy, which should preserve the chemical fingerprint of the early cosmos, contain roughly 3 times more lithium-7 than the Big Bang theory says they should. This is the cosmological lithium problem, and its solution may be written in the interstellar medium we see today. Where did this extra lithium come from? The interstellar gas and dust act as the present-day ledger for this elemental accounting. If the extra lithium was made later in cosmic history, its signature should be mixed into the galactic reservoir. 2 primary astrophysical factories are suspected. The first is cosmic ray spallation, as those high-energy protons and alpha particles we discussed earlier slam into heavier atoms like carbon or oxygen in the interstellar medium. They can shatter them, producing lighter fragments including lithium, beryllium, and boron. This process definitely happens, and it explains the abundances of those other light elements. But detailed calculations suggest it likely cannot produce enough lithium-7 to solve the entire discrepancy, especially at the earliest times. The second factory is stellar nucleosynthesis. Certain types of evolved stars, like asymptotic giant branch stars, can produce lithium in their interiors and then dredge it up to the surface, expelling it into space through stellar winds. Nova, the explosive flares on the surface of white dwarfs, are also prolific lithium producers. Over billions of years, these sources have undoubtedly enriched the interstellar medium with newly forged lithium. Yet the problem is most acute in the oldest stars, which formed before this later enrichment could have taken place. So is the interstellar medium simply a reservoir for lithium made by later generation stars, masking the primordial signal? Or is it a clue pointing to something far more fundamental, a flaw in our understanding of the first 3 minutes of the universe? This leads to the tantalizing possibility that the lithium problem is not an astrophysical puzzle, but a physics one. Perhaps our models of nuclear reaction rates in that primordial inferno are slightly off. Maybe exotic particles from dark matter decayed and altered the nuclear soup. Or perhaps the early universe was not perfectly uniform, with pockets of slightly different density that changed the nuclear yields. The interstellar medium today holds the integrated history of all these potential sources. By measuring lithium abundances in different environments, in young stars, in diffuse clouds, in the gas itself, astronomers are trying to disentangle the primordial lithium from the added contributions. It is a forensic investigation on a galactic scale. The mystery forces us to question our most fundamental narrative. Either our understanding of stellar and cosmic ray production is incomplete, or our picture of the Big Bang itself requires a subtle but profound adjustment. The lithium in the gas between the stars is therefore more than just another element. It is a cosmic anomaly, a quiet but persistent whisper from the dawn of time that says a piece of the story is still missing. What does this one stubborn element reveal about the very first moments of everything? That lithium anomaly is a puzzle of pure elements, but in the dark of space, even simple dust carries a hidden electric charge. Drifting through the galaxy, each microscopic grain is not a neutral bystander. It is a tiny, electrically charged particle, and the exact number of electrons it carries, or lacks, is a critical yet elusive detail. This charge state is a fundamental property, a silent force that governs the grain's destiny and the environment around it. How does a dust grain, alone in the void, become electrified? Two primary processes are constantly at work, fighting for dominance. The first is the photoelectric effect, the same phenomenon that powers solar panels. When a photon of starlight, especially energetic ultraviolet light, strikes a dust grain, it can knock an electron clean off the surface. That electron goes flying off into space, leaving the grain with a net positive charge. The second process involves collisions with the surrounding plasma, the thin soup of free electrons and ions that permeates the interstellar medium. If the grain is initially neutral, a fast-moving electron from the plasma can strike it and stick, giving it a negative charge. Conversely, a positive ion from the plasma might collide and steal an electron from the grain, leaving it even more positively charged. The grain's final charge is a dynamic equilibrium, a minute-by-minute balance between these competing processes. In a bright, harsh environment near a hot star, the photoelectric effect dominates, blasting electrons away and leaving grains positively charged. Deep inside a dark molecular cloud where starlight cannot penetrate, collisions with the cold plasma take over, and grains tend to become negatively charged. This seemingly minor detail has profound and far-reaching consequences. The charge on a dust grain dictates how it interacts with the galaxy's magnetic field. A charged grain will spiral along magnetic field lines, its motion constrained by invisible forces. This affects how grains drift through clouds, how they are distributed, and even how they help to dissipate magnetic energy, a key factor in allowing clouds to collapse. The charge state is also a master regulator of chemistry on the grain's surface. A positively charged grain will attract negatively charged atoms and molecules, like oxygen or certain molecular fragments, altering the reaction pathways that build complex ices. It can accelerate or inhibit the formation of the very molecules that are life's precursors. Perhaps most dramatically, charge dictates whether grains can stick together to grow. Two grains with the same charge, both positive or both negative, will repel each other electrostatically. This repulsion can prevent them from colliding and coagulating, stalling the first crucial step toward building pebbles, planetesimals, and planets. Only if their charges are opposite or if their kinetic energy is high enough to overcome the electrostatic barrier can they merge and grow. The central mystery is that we cannot measure this charge directly from light years away. We infer it from complex models that account for the local radiation field, the density and temperature of the plasma, and the grain's composition. A single miscalculation in the grain's ability to hold onto electrons, a property called the work function, can throw the entire model off. This means a key parameter in the life cycle of dust and the evolution of clouds rests on an estimate. The charge state of interstellar dust is a hidden variable, a silent switch that can determine whether a cloud fragments into stars efficiently or remains in a suspended state, and whether the path to planets is open or blocked. It is a reminder that in the cosmic dark, the smallest details carry an invisible electric weight. These electrically charged grains become the foundation for a delicate, frozen architecture. In the deep, silent cores of molecular clouds, far from the disruptive glare of starlight, a slow-motion frost accumulates on every speck of dust. This is not a simple coating of water ice. It is a layered, complex mantle of frozen molecules: water, carbon monoxide, carbon dioxide, ammonia, and methanol, building up atom by atom over millions of years. The precise recipe of this interstellar ice, however, is a chemical fingerprint we are still learning to read. What determines why one cloud has ice rich in carbon monoxide, while another is dominated by water and carbon dioxide? The answer lies in a combination of local conditions and a painstakingly slow construction process. In the near-perfect vacuum and bitter cold, only a few degrees above absolute zero, gas phase atoms and molecules move sluggishly. When one of these particles, a water molecule, an oxygen atom, a carbon monoxide molecule, happens to collide with a dust grain, it does not bounce off. It sticks, held by weak intermolecular forces in a process called physisorption. It becomes frozen in place, a permanent addition to the grain's growing icy shell. This is not a random pile, however. Surface chemistry on the grain itself plays the director. A hydrogen atom, the most abundant element in the universe, is also the smallest and most mobile. It can tunnel across the icy surface, as we discussed earlier. When it encounters a frozen oxygen atom, they can react to form a hydroxyl group. Another tunneling hydrogen atom finds that hydroxyl, and together they form a water molecule locked into the ice. Similar dances create formaldehyde and methanol from carbon monoxide. The final composition of the mantle, therefore, depends on the availability of different atoms, the temperature of the grain which controls mobility, and the history of the cloud itself. These icy mantles serve a dual, vital purpose. First, they are cosmic refrigerators. The ices are brilliant at radiating away heat in the infrared. This efficient cooling allows the dense core of a cloud to shed the energy released by gravitational collapse, enabling it to grow colder and denser, a critical step toward forming a star. Second, and perhaps more astonishingly, they are protected chemical factories. The icy matrix shields fragile molecules from the destructive power of cosmic rays and provides a solid stage where complex reactions can occur. The frozen water and other molecules are not inert. They are constantly being processed by the faint background radiation and occasional cosmic rays strike, breaking apart and recombining into ever more complex organic compounds. We know all of this because of a single, powerful technique: infrared spectroscopy. When starlight from a background star passes through a dense, icy cloud, the specific bonds in these frozen molecules absorb very distinct colors of infrared light. Each molecule has its own unique absorption fingerprint. A dip in the spectrum at 3 micrometers reveals water ice. A dip at 4.67 micrometers betrays frozen carbon monoxide. By reading this spectral barcode, astronomers can take a remote inventory of the cloud's icy inventory, determining not just what ices are present, but in what ratios, and even whether they are mixed together or form separate layers. These observations tell us that interstellar ices are remarkably common and their chemistry is rich. They are the frozen reservoirs from which the next generation of stars and planets will draw their volatile materials. The mystery of their specific composition is thus a question about the raw ingredients being delivered to infant solar systems. What does the particular blend of ices in a cloud predestine for the chemistry of its future planets and comets? These icy mantles are a frozen prelude to a far more explosive phase. The dense clouds they cool will one day birth the very stars whose deaths will reshape the galaxy on a colossal scale. This grand cyclical drama is captured in a powerful idea known as the galactic fountain model. Picture the disk of the Milky Way not as a static platter of stars and gas, but as a living, breathing entity. Its breath is the collective fury of supernova, and its circulatory system is a vast vertical flow of million-degree plasma. When a cluster of massive stars explodes in relatively quick succession, their individual supernova remnants can merge into a single titanic bubble of hot gas. This bubble, pressurized from within by more explosions and the fierce winds from surviving massive stars, does something extraordinary. It finds the path of least resistance, which is not sideways through the dense galactic disk, but upward, punching through the thinner gas above and below like a volcanic plume. These are the galactic chimneys, colossal conduits that vent this superheated material high above the starry plane, sometimes for thousands of light years. The hot gas, now part of what astronomers call the galactic corona or halo, expands into the vast, almost empty space. But this is not the end of its journey. Isolated in the halo, far from the energetic turmoil of the disk, this plasma begins a slow, inevitable cooling. As it radiates away its immense heat in X-rays, it condenses. Over millions of years, this condensing gas can fragment into the massive, cold clouds of neutral hydrogen we detect falling back toward the disk, the high-velocity clouds we discussed earlier. This is the fountain in action, an explosive eruption, a long, cooling arc, and a final return as a rain of fresh, albeit processed, material. The theory is elegant, explaining how heavy elements forged in stellar cores get redistributed vertically and how the galaxy might replenish its star-forming fuel. But like all grand cosmic models, the devil is in the details, and the observational evidence is challenging to gather. We see the supposed chimneys as faint, vertical structures in X-ray and radio maps, often emanating from regions of intense star formation like the Cygnus X complex. We detect the hot gas in the halo with sensitive X-ray telescopes, and we certainly observe the high-velocity clouds plunging downward. Connecting these dots into a single, continuous cycle, however, requires solving several intertwined mysteries. The first is the cooling timescale. Theoretical models suggest that for the fountain to work efficiently, the hot gas must cool and condense within a few 100 million years, roughly the time it takes to complete its fountain arc. But is it cooling fast enough? The hot plasma is extremely tenuous, making it a poor radiator. Certain ions, like oxygen 6 and 7, are brilliant coolants, but their abundance is uncertain. If cooling is too slow, the gas might never condense into clouds. It would simply form a static, hot halo. The second mystery is mixing. When this cooled gas falls back, it must seamlessly blend with the different phases of the interstellar medium in the disk, the warm neutral hydrogen, the molecular clouds. How does this integration occur without simply triggering more violent shocks and reheating? Does it drizzle in gently or slam down in disruptive sheets? Finally, there is the question of mass and energy circulation. Is the fountain the dominant process recycling gas, or just one of several? What fraction of all supernova energy goes into lofting this material versus heating the disk or driving turbulence? Each unanswered question is a gap in our understanding of the galaxy's metabolism. This model portrays the Milky Way not as an island universe, but as a stormy world with its own weather patterns, where the rain that feeds future stars is first distilled in the scorching plumes of stellar death. But the faint, ionized haze of the warm ionized medium holds a subtle radio whisper that defies simple explanation. Deep within the diffuse, lukewarm plasma that fills so much of our galaxy, atoms are constantly playing a game of capture and release. Electrons, stripped away by starlight, wander freely until they are slowly recaptured by a lonely proton, reforming a simple hydrogen atom. This act of recombination should be a quiet affair, but in the thin gas of space, it sometimes sings a very specific song. When an electron is captured not into the atom's lowest energy level, but into a shockingly high one, perhaps the 100th or even the 1000th rung on the quantum ladder, it creates an atom in a bizarre, oversized state. Physicists call it a Rydberg atom. This fragile, puffed-up atom cannot last. The electron immediately begins a cascading fall down the energy ladder, jumping from one high level to a slightly lower one with each step. And with each quantum jump, it emits a photon of radio waves at an exquisitely precise frequency. These are the radio recombination lines. They should be a perfect diagnostic tool, a direct readout of the temperature, density, and ionization state of the diffuse gas. Yet when astronomers point their most sensitive radio telescopes at the sky, they find a persistent and puzzling mismatch. The observed strengths of these lines are often far weaker than our best models predict. It is as if we are listening to a distant orchestra and whole sections of instruments are playing much softer than the score dictates. This discrepancy is the radio recombination line enigma, and it points to a fundamental gap in our understanding of the most common ionized environment in the galaxy. The leading suspicion is that the gas is not in a placid, steady state. Our models assume a calm equilibrium where ionization and recombination are perfectly balanced. But what if the warm ionized medium is constantly being shocked, stirred, or unevenly illuminated? If the gas is being heated or ionized in sudden, transient bursts, perhaps by the fading shockwaves of ancient supernovae or the turbulent mixing at cloud boundaries, the electrons might have more energy than we account for. This could affect the delicate quantum mechanics of how they are captured, skewing the statistical likelihood of forming those high, singing Rydberg states in the first place. Another possibility involves the very shape of the emitting regions. The models often assume simple, uniform clouds. In reality, this ionized fog is likely a fantastically complex froth, filled with tiny, dense filaments and vast, empty voids. The recombination lines might be emanating only from the denser wisps, while our observations average over large volumes that include mostly empty space, diluting the expected signal. There is even a chance that a significant portion of the ionizing radiation is not the steady ultraviolet glow of stars, but something more exotic and intermittent, like low-energy cosmic rays or the conductive interfaces between different gas phases. Each of these scenarios paints a picture of a far more dynamic and stormy warm ionized medium than we have imagined. Solving this enigma requires a new generation of radio telescopes with unprecedented sensitivity and resolution, capable of mapping these faint lines across the sky and correlating them with maps of X-ray emission, ultraviolet glow, and magnetic fields. It is a meticulous forensic task, listening to the faint radio hum of recaptured electrons to decode the hidden weather patterns within the galaxy's ionized atmosphere. This quiet signal, then, is more than a technical curiosity. It is a discordant note in our symphony of the interstellar medium, a clue that the gentle ionized fog is alive with subtle, non-equilibrium physics we have yet to chart. What other secrets might be hidden in the precise pitch of this atomic radio song? That faint radio song hints at a hidden, volatile temperament. While we often picture the interstellar medium as a slow-motion ocean, changing over millions of years, it may also host sudden, brilliant flashes that vanish in an instant. These are not the predictable cycles of stars, but transient events, unpredictable flares that could illuminate the darkness in ways we are only beginning to hunt for. Imagine a flash of gamma rays from a neutron-star merger. its afterglow briefly painting the surrounding gas with X-rays, or consider the possibility of immense discharges within dense molecular clouds, a kind of cosmic lightning born from built-up static electricity between dust grains and ions. Even the sudden ignition of accretion around a previously quiet black hole could flood its local neighborhood with a burst of radiation, momentarily ionizing a cloud light years away. These events would be fleeting, lasting from seconds to days, and utterly unpredictable. They represent a hidden, dynamic side to the interstellar environment, one that traditional astronomy focused on steady objects has largely missed. The key to finding them lies in a new way of watching the sky: time domain surveys. Projects like the Vera-C Rubin Observatory will scan the entire visible sky every few nights, not just once, but over and over for a decade. They will create a colossal movie of the universe, alerting astronomers to any point of light that changes, brightens, or appears where nothing was before. This constant vigilance could catch the interstellar medium in the act of responding to a distant cataclysm. A dark cloud might suddenly fluoresce as a shockwave of radiation passes through it, or a knot of gas might briefly glow in a specific color as it is heated by a transient event. These flashes would be more than just celestial fireworks. They would be probes. The way a cloud lights up and fades can reveal its density, composition, and structure in exquisite detail, much like a lightning bolt illuminates the interior of a storm cloud for a split second. A transient event provides a sudden, intense burst of energy that acts as a perfect experiment, allowing us to see how the interstellar medium reacts under extreme and sudden stress. Furthermore, if phenomena like large-scale electrostatic discharges truly occur, they could be a potent source of energy for chemistry, potentially forging unique molecules in an instant of spectacular violence. The mystery, then, is one of timing and scale. How often do these interstellar flares happen? Are they common, flickering across the galaxy like heat lightning on a summer night, or are they rare, century-spanning events? And what would such volatility mean for the delicate chemical factories we know exist within clouds? Could a single, nearby flash erase eons of slow molecular buildup or catalyze a new pathway altogether? The search for these transients transforms our view of the space between stars from a placid backdrop into a potential stage for sudden, dramatic performances. It suggests that if we watch patiently enough, the darkness itself might occasionally reveal its secrets in a brilliant, fleeting flash. What might we see in that sudden, unexpected light? Even the simplest atoms can hold a cosmic contradiction. Among the lightest elements born in the Big Bang, deuterium holds a special place. It is an isotope of hydrogen, but with a crucial difference. Its nucleus contains not just a single proton, but a proton bound to a neutron. This heavy hydrogen is a fragile relic. It was forged only in the first few minutes of the universe, and unlike the elements created in stars, it cannot be made in any significant quantity by known astrophysical processes. In fact, stars only destroy it. This makes deuterium a perfect fossil, a pristine tracer of the universe's original chemical composition. By measuring how much deuterium exists today in the local interstellar medium, we should get a direct reading of that primordial value. Yet when astronomers make that measurement, they find a puzzling shortfall. The amount of deuterium we see in the gas around us is noticeably lower than what our best models of the Big Bang predict. This is the deuterium abundance puzzle, and it forces us to question how thoroughly the galaxy has stirred its ingredients over billions of years. The reason for the discrepancy points directly to the galactic life cycle. Deuterium is exceptionally vulnerable. When a cloud of gas containing deuterium collapses to form a star, that deuterium is carried into the stellar furnace. Inside the star's core, where temperatures and pressures are immense, deuterium nuclei are incredibly efficient fuel. They fuse with protons at a much lower temperature than regular hydrogen does. In fact, in a star like our Sun, Any deuterium in the core is completely burned away in the star's first few million years, long before it even reaches the main sequence. This process is called astration, the locking away or destruction of an element inside stars. Every generation of stars that forms consumes a portion of the galaxy's primordial deuterium, converting it into helium-3 or other products. Over the 13.8 billion-year history of the Milky Way, countless stars have formed, lived, and died. They should have systematically depleted the galactic reservoir of this fragile isotope. So the fact that we see any deuterium at all in the interstellar gas is remarkable. It means some primordial gas has never been cycled through a star. But the puzzle is one of accounting. The observed local abundance is lower than the primordial prediction, which aligns with the idea of astration. However, the exact amount of the shortfall is critical. It tells us how much of the gas in our neighborhood has been processed through stars versus how much remains in its original, pristine state. The leading explanation is one of incomplete mixing. Our solar system does not float in a perfectly homogenized galactic soup. We are inside the local bubble, a region shaped by recent supernovae, and we are passing through the local interstellar cloud. This gas is likely a specific sample, a particular mix of material that has been heavily processed. It could be enriched with the ashes of many stellar generations, which would be low in deuterium. Meanwhile, elsewhere in the galaxy, perhaps in the outer disk or in the high-velocity clouds falling from the halo, there could be vast reservoirs of much more pristine gas, rich in deuterium, that has not yet blended with our local environment. The deuterium we measure is just a local snapshot, not the galaxy's average. This interpretation places deuterium at the heart of a grander mystery about galactic chemical evolution. If incomplete mixing is the full answer, then mapping the deuterium abundance across different regions of the Milky Way should show wild variations. In old, recycled gas near the galactic center, deuterium should be very low. In the infalling, unprocessed gas of the high-velocity clouds, it should be nearly as high as the primordial value. Observations from spacecraft like the Hubble Space Telescope, which can measure deuterium by its unique fingerprint in the ultraviolet absorption lines of distant stars, are beginning to test this. The data so far is complex and somewhat contradictory, showing more uniformity than some mixing models predict. This raises the other, more profound possibility. What if our understanding of how deuterium is destroyed needs revision? Could there be additional, unknown destruction mechanisms in the interstellar medium itself? Perhaps in certain violent environments, like the interfaces of hot bubbles and cold clouds, or in the intense radiation fields near supernova deuterium could be broken apart without ever entering a star. Or could our models of the Big Bang itself, which give us that pristine predicted value, require a subtle tweak? The weight of this one light atom is immense. It serves as a gauge for the galaxy's history of star formation and mixing. A lower local deuterium abundance suggests our corner of the Milky Way is built largely from recycled stellar material, the ashes of long-dead stars. A higher abundance, if found elsewhere, would point to fresh, primordial infall. By chasing this discrepancy, we are not just solving a chemical puzzle. We are tracing the circulatory system of the entire galaxy, trying to determine if it is a well-mixed pot of stew or a collection of distinct recipes that have never fully blended. The answer defines how we see our own origins. Are we and our solar system made from material that has cycled through many stellar generations, or are we forged from older, more pristine stuff? The deuterium in the thin gas around us holds the record of that ancient inheritance, a faint signature slowly being erased by the very stars it helps to create. The faint radio hum of recaptured electrons is a whisper compared to a far more visible clue written in the very light of the stars. Look up at the Milky Way on a clear, dark night, and you see a river of scattered light. But to a sensitive telescope equipped with a polarizing filter, that river reveals a hidden current. The starlight is polarized, its light waves oscillating in a preferred direction across the sky. This is not a property of the stars themselves. It is a message from the interstellar medium imprinted during light's long journey. The messengers are those countless microscopic dust grains, and their alignment is one of the most elegant yet stubborn puzzles in astrophysics. For starlight to become polarized, the dust grains blocking it cannot be perfect little spheres. They must be asymmetrical, elongated, or perhaps flattened like tiny cosmic needles or frisbees. And crucially, they must be aligned, their long axes pointing in roughly the same direction over vast distances. If they were tumbling randomly, they would scatter light in all directions, leaving no net polarization. The fact that we see a strong, coherent signal means something is organizing them. For decades, the prime suspect has been the galaxy's magnetic field. The theory is beautifully simple. If these irregular grains contain even a trace of ferromagnetic material, or if they carry an electric charge, they would act like microscopic compass needles. The weak interstellar magnetic field would exert a torque, causing them to spin with their long axes perpendicular to the field lines. Starlight passing through this forest of aligned grains would have its electric field vector preferentially absorbed in one direction, emerging polarized. This alignment is our primary tool for mapping the Milky Way's invisible magnetic skeleton. By measuring the angle of polarization for millions of stars, we can trace the field's direction as it flows along spiral arms, wraps around bubbles, and weaves through clouds. But the elegance of the idea masks a ferociously complex reality. The leading physical model to explain how this happens is called radiative alignment torque. It is a dance between starlight, spin, and magnetism. Imagine an irregular grain drifting in space. It is bathed in starlight from all directions, but rarely evenly. If one side of the grain absorbs or scatters more light than another, the photons impart a tiny, physical push radiation pressure. Because of the grain's shape, this push is not balanced. It creates a net torque, causing the grain to spin. Now introduce a magnetic field. If the spinning grain has even a minuscule magnetic moment, the field interacts with it, just like a child's spinning top processes in Earth's gravity. This interaction gradually forces the grain's axis of rotation to align with the magnetic field direction. It is a slow, relentless process, but over thousands of years it can bring order to chaos. The problem is, the math is extraordinarily difficult. The outcome depends on a dizzying list of variables: the grain's exact shape, size, composition, and temperature, the spectrum and directionality of the local starlight, the strength of the magnetic field, and even the grain's internal structure. Is it a solid lump or a fluffy aggregate? Change one assumption, and the predicted alignment can vanish or even point the wrong way. Observations constantly challenge the theory. We see polarization even in dark molecular clouds where starlight is exceedingly faint, raising the question of whether radiative torques are powerful enough there. In some regions, the pattern of polarization suddenly twists or becomes disordered, suggesting the alignment mechanism has broken down, perhaps due to extreme turbulence or shocks. Furthermore, laboratory experiments cannot yet recreate the exact conditions of deep space to test these models directly. We are relying on supercomputer simulations that must simplify an impossibly complex natural phenomenon. This leaves a critical question open. Are magnetic fields truly the sole director of this cosmic ballet, or could other forces, like the flow of gas itself, also play a role in certain environments? The alignment of interstellar dust is therefore a dual mystery. It provides our best map of the galaxy's hidden magnetic forces, yet the very mechanism that creates the map is still under construction. We are using a tool to explore the unknown, while still arguing about how the tool itself works. What other secrets of magnetic fields might be hidden in the precise twist of a polarized starlight wave? The polarized light we see is a delicate tracer of order, but the interstellar medium is also shaped by the most violent events in the galaxy. When a massive star exhausts its nuclear fuel, its core collapses in a cataclysm that outshines an entire galaxy for a few brief weeks. The supernova explosion blasts the star's outer layers into space at speeds exceeding 10,000 kilometers per second, creating a spherical shockwave of unimaginable power. This is not a mere disturbance, it is a cosmic tsunami, and its collision with the surrounding interstellar medium is a violent, creative, and deeply mysterious interaction that forges the future of the galaxy. The expanding shell of debris, the supernova remnant, plows into the gas and dust like a titanic snowplow. At the leading edge, the shock front is a place of extremes. The gas ahead of it is suddenly, brutally compressed by a factor of hundreds or thousands, heated to millions of degrees in an instant. It glows fiercely in X-rays, a visible scar of the violence. Within this chaotic zone lies one of the greatest puzzles, the birthplace of galactic cosmic rays. The shock wave itself is a natural particle accelerator of staggering efficiency. Theorists believe that charged particles, like protons, can become trapped by turbulent magnetic fields at the shock front. They bounce back and forth across this boundary, gaining a little more speed with each crossing until they are flung out into the galaxy with nearly the speed of light. This process, called diffusive shock acceleration, is our best explanation for the origin of these high-energy particles. Yet, despite decades of searching, we lack definitive proof. We see gamma rays from supernova remnants, but are they from protons smashing into gas or from electrons spiraling in magnetic fields? Finding that smoking gun remains a holy grail of high-energy astrophysics, a test of whether these stellar cataclysms are the primary engines powering the galaxy's invisible particle radiation. But the violence of a supernova is not purely destructive. As the shock wave compresses the surrounding interstellar gas, it can trigger a paradoxical act of creation. Imagine a relatively quiet, stable cloud of hydrogen. The supernova blast wave slams into it, crushing the gas to much higher densities. In some regions, this sudden compression can overwhelm the cloud's internal support, its thermal pressure, its turbulence, its magnetic fields. Gravity, waiting for its chance, seizes control. The compressed knot of gas becomes unstable and begins to collapse, igniting a new generation of stars. We see evidence for this in places like the Orion Nebula complex, where the brilliant young stars are nestled right up against the expanding shell of a much older supernova remnant. It is a stellar feedback loop on a grand scale. Massive stars die in explosions that give birth to new stars, some of which will themselves become supernova. This process seeds heavy elements forged in the progenitor star into the next stellar nursery, enriching the cosmic chemistry. The shockwave also sweeps up vast amounts of interstellar dust, the very dust we discussed earlier. Some grains are vaporized in the inferno, returning their atoms to the gas. Others might survive, only to be shattered into smaller fragments or coated with new layers of material. The remnant becomes a colossal blender, churning and reprocessing the galactic ingredients. On the largest scale, the work of a single supernova is just a prelude. In regions where massive stars are born in dense clusters, they live fast and die young in a rapid sequence. Their individual supernova remnants merge and their powerful stellar winds combine to carve out a single gargantuan cavity in the interstellar medium. These are superbubbles, structures that can span hundreds or even thousands of light years. Our own solar system floats inside one, the local bubble. These bubbles fundamentally reshape the galactic landscape. Their hot, tenuous interiors are filled with million-degree plasma, while their sweeping shells are dense walls of accumulated gas and dust. As they expand, they can break out of the galactic disk entirely, venting hot gas and metals into the galactic halo in a galactic fountain. This process redistributes energy and material on a phenomenal scale, stirring the galactic pot and preventing the interstellar medium from settling into a quiet, uniform state. The superbubble shell, a sweeping arc of compressed material, can itself become the site for triggered star formation on a colossal scale, potentially giving rise to new star clusters. Yet mysteries abound. How efficiently do these bubbles actually transport energy? How much of their hot interior gas cools and condenses to fall back as rain versus escaping the galaxy forever? The interaction of a supernova with the interstellar medium is therefore the ultimate story of death and rebirth. It is a destructive force that scatters ashes, but from those ashes it compresses the material for new suns and sculpts the very architecture of the galaxy itself. In the end, the space between the stars remembers every explosion, carrying the scars and the seeds of countless stellar lifetimes in its turbulent, ever-changing flow. The magnetic fields and supernova that shape the galactic landscape also hide a fundamental accounting error in our cosmic ledger. For decades, astronomers have mapped the galaxy's star-forming fuel using a trusted proxy, the radio emission from carbon monoxide molecules. Where you find carbon monoxide, you find the dense, cold molecular hydrogen gas that collapses to form stars. It is a reliable partnership, or so we thought. But a deeper look reveals a troubling discrepancy. When we compare maps of interstellar dust, which traces total gas mass, with maps of gamma-ray emission, which is produced when cosmic rays strike atomic nuclei, a glaring gap emerges. There are vast regions of space where the dust and gamma rays tell us significant mass is present, yet the carbon monoxide maps show nothing but emptiness. This missing material is called dark gas, and it represents a hidden ocean of molecular hydrogen that our traditional telescopes have been blind to. The leading theory is both simple and revolutionary. Molecular hydrogen itself is incredibly difficult to detect directly in the cold depths of space. It lacks a strong, convenient emission line like carbon monoxide's, so we have always relied on carbon monoxide as a tracer, assuming that wherever there is enough hydrogen to form molecules, there will also be enough carbon and oxygen to form carbon monoxide. But what if that assumption is wrong? In the outermost, less dense fringes of molecular clouds, the environment may be just right to shield hydrogen molecules from dissociating starlight, but still too harsh for carbon monoxide to survive. Ultraviolet radiation can break apart carbon monoxide molecules more easily than hydrogen molecules in these transitional zones. The result is a vast shroud of dark molecular hydrogen, a ghostly fuel reserve that wraps around every known cloud, invisible to our standard radio surveys. We only infer its presence because cosmic rays, those high-energy particles, still smash into its hydrogen nuclei, producing the gamma rays we detect. And interstellar dust, mixed evenly with the gas, still absorbs and reddens starlight, revealing its mass. This dark gas could account for a staggering amount of material, perhaps as much as 30% of the entire molecular mass of the galaxy. Its existence forces a complete recalibration of our galactic inventory. Where we once saw the sharp edges of star-forming clouds, we now see only the bright cores surrounded by a massive, unseen halo of potential. This changes our understanding of how clouds grow and evolve. Does star formation begin in these dark, carbon monoxide-free outskirts before the gas condenses enough to show up in our maps? Could this be the reservoir from which clouds feed, slowly accumulating this stealth material before a trigger condenses it into a visible core? The implications ripple outward. If we have been missing this much of the galaxy's molecular content, then our estimates for the star formation rate, both in our galaxy and in distant ones, might be systematically too low. The dark gas problem is a humbling reminder that our view of the cosmos is limited by the tools we use to see it. We have mapped the galaxy in the light of carbon monoxide, but we have only been sketching the bones, missing the full body of its star-forming potential. What other invisible structures vital to the galactic cycle remain hidden in plain sight, waiting for us to ask the right question? Hidden within the galaxy's own radiostatic, there is a signal that defied explanation for a single tantalizing moment. On a summer night in 1977, a radio telescope in Ohio known as the Big Ear was listening to the sky. Its computer printout, scrolling with numbers and letters representing signal strength, recorded something extraordinary. For 72 seconds, a narrowband radio signal, billions of times stronger than the cosmic background, blared from the direction of the constellation Sagittarius. An astronomer named Jerry Amon, reviewing the data, circled the alphanumeric sequence in red pen and wrote a single, powerful word beside it. Wow, the signal was never heard again, despite dozens of follow-up searches. The WOW signal stands as the most famous candidate for a potential interstellar message, a ghost in the machine of our search for cosmic company. But could the vast, complex interstellar medium itself be the source of such enigmatic whispers? The idea of space as a communication channel is a captivating thought experiment. The thin gas and dust between stars is not a perfect vacuum. It is a plasma filled with free electrons and ions that can amplify, scatter, and distort radio waves. Natural cosmic mazes, like those found in the swirling gas around newborn stars, can produce incredibly bright, narrowband radio emission, mimicking the kind of signal an engineered transmitter might produce. Intense magnetic fields around pulsars create sweeping lighthouse beams of radiation. Even the turbulent interactions within the interstellar medium can generate bursts of coherent emission that, to our algorithms searching for patterns, might appear ordered. The challenge for scientists engaged in the search for extraterrestrial intelligence is the ultimate game of cosmic forensics, distinguishing a natural fingerprint from an artificial one. Every signal must be vetted against the known orchestra of the interstellar medium. Does its frequency drift in a way consistent with the Doppler shift caused by a planet's rotation and orbit? Does it pass through multiple, independent telescopes to rule out local interference? The interstellar medium itself becomes both the medium and the mimic. Its very properties that could carry a signal across light years. Its ability to transmit certain radio frequencies with minimal absorption are the same ones that can, under specific and rare conditions, generate false alarms. This does not diminish the wonder of the search, it deepens it. It means that to find a true message, we must first become fluent in the natural language of the galaxy. We must understand the hiss of hydrogen, the chirp of a pulsar, the flare of a stellar magnetar, and the whisper of spinning dust. Only by mapping the full spectrum of natural noise can we hope to recognize a syllable that stands apart. The interstellar medium, therefore, presents us with a speculative mystery of profound beauty. It is the ultimate cosmic backdrop against which any deliberate signal would have to declare itself. Its chaotic, generative nature means it will always produce strange and wonderful emissions, keeping our curiosity alive. But it also means that if a signal ever does break through that is unmistakably engineered, its clarity against that complex background would be the most powerful statement imaginable, a message not just sent but crafted to be heard over the eternal hum of the galaxy itself. What other brief, brilliant anomalies are waiting in decades of radio data, hidden within the static of the stars? The search for signals within the static leads us to a final, ultimate question of scale. Every mystery we have explored, the chemistry on dust grains, the violence of supernovae, the hidden reservoirs of dark gas, is a single note in a symphony playing out over billions of years. This forces us to look ahead to the destiny of the interstellar medium itself. What is the final chapter for this cosmic ocean? Will the galaxy one day simply run out of breath? The answer lies in a slow, grand competition between consumption and replenishment. Star formation is a voracious process. Every new star, from a tiny red dwarf to a brilliant blue giant, locks away a portion of the galaxy's gas for millions or even trillions of years. Supernova and stellar winds return some of this material, but it is a messy, inefficient recycling. A significant fraction of the gas is forever trapped in long-lived, low-mass stars, in stellar remnants like white dwarfs and neutron stars, and in the planets and rocks that orbit them. With each generation of stars, the total reservoir of available fuel slowly dwindles. If this were the only process at work, the fate of the Milky Way would be a quiet, fading twilight. Astronomers call such a future red and dead, a galaxy where all the bright, blue, short-lived stars have long since burned out, leaving only the cooler, older red stars to shine faintly as the last embers. The interstellar medium would be a thin, exhausted ghost, unable to spark new stellar fires, but the galaxy is not a closed box. The story is not one of simple exhaustion. Two powerful forces work against this fading. The first is the galactic fountain we discussed, the magnificent cycle that lifts hot gas into the halo only to have it cool and fall back as a rejuvenating rain. This process does not create new matter, but it does stretch out the timeline, ensuring that gas is used and reused many times over, maximizing its potential. The second force, however, is truly external, accretion. Our galaxy is still growing. It is constantly gathering fresh, pristine hydrogen from the cosmic web, the vast filamentary structure of dark matter and gas that spans the universe. This inflow comes in the form of the high-velocity clouds we see plunging from the halo, and possibly from the slow, steady siphon from the hot corona that surrounds the Milky Way. This is new fuel, gas that has never been cycled through a star, rich in the primordial elements. It is the galaxy's lifeline. The ultimate fate of our interstellar medium, therefore, depends on the balance between this incoming rain and the relentless consumption by star formation. Current observations suggest that for the Milky Way, the inflow and the outflow are nearly in balance. We are in a relatively stable, mature phase. Star formation continues at a modest pace, and the great cycle of death and rebirth churns on. But this equilibrium will not last forever. As the universe expands and the cosmic web stretches thinner, the supply of fresh, cool gas to galaxies will gradually slow. Furthermore, as the galaxy's stellar population ages, the rate of violent supernova will decrease, potentially making the fountain less vigorous. The interstellar medium will become gradually more enriched with heavy elements and over tens of billions of years more diffuse. The brilliant spiral arms, fueled by waves of dense gas, may eventually fade and settle. So what is the final answer? The interstellar medium will not vanish, but it will transform. It will become a quieter, hotter, more uniform sea, with fewer cold, dense pockets where new stars can be born. The great spiral dance will slow. The galaxy's story, written in gas and dust, is one of a slow burn, not a sudden extinguishment. We are living in its vibrant Middle Age, a time of fertile chaos between the fiery birth of the first stars and the long, calm fading of the last. This grand perspective makes every mystery we have walked through feel more poignant. The complex chemistry on a dust grain, the flash of a supernova, the silent fall of a high-velocity cloud, these are not isolated events. They are the individual heartbeats of a galaxy that is very much alive, breathing in, breathing out, and slowly writing its own eventual, quiet end across the deep time of the cosmos. Our journey through 30 mysteries reveals a galaxy transformed. The darkness between the stars is not a void but a frontier. It is a cosmic ocean of turbulent gas, ghostly dust, and invisible forces. A place where chemistry brews in the cold and where the birth and death of stars sculpt the landscape of existence. Every unanswered question we have encountered, from the identity of the molecules stealing starlight to the source of the galaxy's missing matter, is a thread in a single, magnificent tapestry. Solving these puzzles is not an academic exercise. It is the key to understanding where we came from. The interstellar medium is the cradle for new solar systems, the factory that forges the complex organic compounds that rain down on young worlds, and the dynamic engine that drives the evolution of galaxies themselves. To comprehend it is to trace our own lineage back to the hearts of ancient supernovae and the frozen clouds that birthed our sun. So the next time you stand beneath a clear night sky, look past the bright points of light. See the darkness for what it truly is, a living, breathing entity, the canvas upon which the story of the cosmos is written. Keep asking questions, stay curious, and remember that the greatest discoveries often begin by wondering about the spaces in between. For more journeys to the edges of our understanding, subscribe and join us as we continue to explore the deepest mysteries of the universe.